All right. Good afternoon, everybody. Um, so last time we saw basic logical connectives, the and, or, and negation, and we also added in a few more connectives, less basic ones if you wish, the XOR, implication, and by implication. All these connectives are defined by truth tables, right? So for instance, if we look at the and, right? So if we have P and Q, we have two Boolean variables, P and Q. The possible truth values for P and Q are true, 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 false, false, true, false, false. And so the values of the and, in this particular case, that's how we define this connective, is that it's true precisely when both P and Q are true. Otherwise, the value is false, right? And for the or, I'll just add in the or right next to in the same truth table here. So what about the or? This is true whenever at least one of them is true or both, right? And so this is false when both P and Q are false, okay? And so on for the other ones, okay? So today we're going to discuss topics related to the notion of truth table. So let me switch screens here, and let's go to our slides. Okay. So we've been building compound propositions, and we're going to say that two compound propositions are logically equivalent, if they have the exact same truth table. Okay, if we have two propositions P and Q which are logically equivalent, we will write P 3 horizontal bars Q's. It looks like an equality, but with an extra horizontal line. So here's a very simple example of two compound propositions. They're very small compound propositions. They're barely compound. So the first one is just a Boolean variable P, and the other one is the negation of P. So these are actually logically equivalent. And if you think about it, this makes sense, right? If you negate the negation, you're basically canceling out the negation. So that's what this says. So if you look at the truth values for P, it can be true or false. Negation will flip those values. And when you negate a second time, it will flip back to the original value. So you see that the values of P and not P are exactly the same. So that's a very, very basic example of logically equivalent propositions. When we are trying to figure out if two compound propositions are logically equivalent, we'll have to build truth tables. That's the simplest way, let's say, to verify that two compound propositions are equivalent. So one trick which is very useful is to introduce intermediate columns. So I'm just going to show you a very small example. So here, suppose that I have the compound proposition P or not Q that I want to build a truth table for this. So I'm going to start by building not Q. That's one of the building blocks of the compound proposition, right? So if you look at this, obviously not Q doesn't depend on P. So all you have to do is look at the values of Q. It flips the value of Q. And once I have not Q, I can then create P or not Q just looking at those columns, right? I don't have to look at the column Q anymore. So these are the truth values, or if you want, the truth table of the proposition P or not Q. Here's one which is a bit more involved, right? So we have the compound proposition P or not Q implies P and Q, and I'd like to know what the truth table of this proposition is. So I'm going to build I'm going to create the truth table of the building blocks of this proposition. I'll start with not Q. That's easy. So I just have to flip the values of Q. Once I have not Q, I can build P or not Q, right? Looking at the columns P and not Q. Then the second thing that I need to build is P and Q, right? So I build that, as we know, as defined with the and from the columns P and Q. And once I have those two columns, P or not Q and P and Q, I can then compute the implication of these, right? If you remember the definition of the implication, this will be true unless the hypothesis, which is in our case, P or not Q, is true here, for example, and the consequence here is false. So this becomes false. So if you have true, false, then the implication will be false. Otherwise, it's true. So this is the truth table of this compound proposition right here. Okay? All right. So yeah, one thing which is really important to, and this is a common mistake that I've seen. You have to be very careful with this. When you have a compound proposition and you want to build its truth table, you need the correct number of rows, right? So what is that? Well, you're going to look at how many different variables appeared in your compound proposition, right? And let's call that little n. Then the number of rows in your truth table is 2 to the power n. So if you have, let's say, 2 variables, then 2 power 2 is 4. You'll have 4 rows. These are 4 different assignment of truth values to your 2 variables. If like in the example here, you have 3 different variables, then you have 2 power 3, which is 8 rows. And you have all the possibilities here for true and false values for P, Q, and R. Okay, so be careful with that. So here is an example of logical equivalence. We'd like to verify that these two compound propositions are equivalent. So on the left in blue is P XOR Q. And on the right, we have not P and Q or P and not Q. Okay. So how do you verify that two compound propositions are logically equivalent? The definition is same truth table. So you compute the truth tables. Okay. So let's compute. So I'm going to handle the red proposition here. So I split it up into pieces. So not P and Q, I can compute. I didn't compute not P. I could have added in here. Once you get used to these logical connectives, you can go a little faster, but please be careful. So not P and Q, you can compute that easily, and you'll see that you get that table right there. Then we'll compute P and not Q. That's also as easy to compute. And then you take the OR of these two, right? And again, remember, OR will be true as long as one of the two is true. So this is what you get for the right-hand proposition. And then the blue part, the XOR, which is previously defined, right? And you see that you have exactly the same table. It's exactly the same values. So if you remember last lecture, I said that all you needed to build any truth table possible are or, and not, right? Essentially, that's all you need. And here is an instance of this where the XOR, you see that you don't need the XOR per se by itself, because you could actually just use or, and not to build it. But the expression is large, right? And XOR is a natural logical connective, so we gave it a special name. It's a shorthand for that more complicated expression, if you wish. Okay, but it's just to illustrate the point that you can express XOR only with those three connectives that we introduced first. I'll leave you as exercises the following equivalences. Biconditional is logically equivalent to P implies Q and Q implies P. If you take a look at that lecture, when I introduced biconditional, I made a very fast little comment about this, and I said that you can define it in terms of implication. And in turn, implication can be defined using negation and or. So if P then Q, or P implies Q, is logically equivalent to not P or Q. And another way of writing the XOR is the negation of P if and only if Q. Okay, so that's another way of writing it. So you should sit down at some point and or just pause this video and prove these for yourselves. Okay, a few more definitions. What's a tautology? So a tautology is a proposition which is always true, whatever the value of its variable. So basically its truth table is all true. Okay, so that's the name we give to a proposition like that. Okay, so it's a tautology. Here's an example of a tautology: P or not P. So this is always true. Whatever P is, this will always turn out to be true. Okay, and you can see it just by computing the truth table, right? So if P is true, then when you take P or not P, then that has to be true. And if P is false, that will make not P true, and then P or not P will be true again, right? So tautology, P or not P. A contradiction, that's, I mean, okay, don't repeat this, but I'm just, this I put there because like I'm supposed to, but it's really not that useful. But anyway, you might see the term. So a contradiction, what is that? It's a proposition which is always false. So think tautology, always true, contradiction, always false. Okay, so here's an example of a contradiction: P and not P. So whatever the value of P is, then this will always turn out to be false, right? So, and I mean, you can think about it in a logically: P and not P. P, you know, the and is true when both are true, but P and not P obviously cannot always be both true. So this will always be false. Or you just compute the truth table, right? That's the same thing. Okay. Okay, so this hopefully makes perfect sense to you. If you have a compound proposition P, it is a tautology precisely when not P is a contradiction. These mean exactly the same thing. Okay, this is not very deep. Okay, just think about it and you say, yeah, okay, yes, right. It's always true. If you negate, always false, right? So, okay, and I put an example. So the negation of P or not P should be a contradiction because P or not P is a tautology. Now I added something interesting, which is that, yeah, we didn't discuss this before, but okay, what the hell? You might you might remember that I made an analogy. I mean, I said there's a very deep analogy between union, intersection, and complementation for sets, and or negation. And in fact, yeah, so De Morgan's laws are valid in this context also. And so it turns out if you take the negation of P or not P, you can apply the analog of De Morgan's law, which will give you not P and not P. And we know that not P is logically equivalent to P. So it turns out that the negation of P or not P is logically equivalent to P and not P, which we know is a contradiction. We saw that earlier. But don't worry too much about that, please. Not sure why I put that in at this point. Anyway, okay, this one. Okay, so here's something which is a bit more subtle. So you might have to think about it a little bit more. Okay, but once you understand the principle, you say, okay, this makes perfect sense. Okay, so this is called the principle of substitution. And so here's what we want to do. So suppose you have a proposition, which I called here phi, and it has variables, which are P, Q, R, maybe others, okay? And here's what I want to do. So I'm going to substitute in this compound proposition phi, sorry. I'm going to replace the variable P everywhere by a new proposition P1. It could be some complicated thing, but I replace every variable P by the same proposition P1. And for Q, I take the variable Q and I replace all the Q's in my proposition by a new proposition P2, same one for each Q. And I do that for every variable. I just substitute for each variable, I substitute a new proposition, and I'm being consistent. If I replace the variable P by a proposition is the same for every P which appears in phi. Now, I'm going to get a new proposition, probably more complicated, right? But one thing is for sure, is that if I started off with a tautology, then the new proposition will also be a tautology, okay? So this is called the principle of substitution. And this is an important and powerful principle. So let's illustrate that with an example, and hopefully you'll see why this is true, and that makes sense. Okay. So I'm going to start with a tautology, which is P or not P. We saw that earlier. And again, this should make sense, right? P or not P, this is always true, whatever the value of P is, okay? So that's what a tautology is. Whatever the value, in this case, we have just a single variable P. Whatever the value of P, this is always true. So suppose that I replace P by some really very complicated expression, then whatever the value of the variables for that expression, the expression will be either true or false. It'll be the same for wherever I replaced in P. And so this will still always be true, right? So that's what the principle of substitution says. Okay, so if I replace P in there by anything, the same thing for each P, right? Then it's not going to change the truth value of the whole new proposition. Has to be true all the time. Okay, so suppose, for example, that I replace P by, it could be anything, Q and R. I just take Q and R, okay? So I get the new proposition Q and R or not Q and R. So whatever value you give to Q and R, right, the value for Q and R on both sides will be the same, right? So it has the form P or not P, so it has to be true. So that's what the principle of substitution says, okay? All right. Here are now two, this is important. Not that the rest wasn't, but like this is like extra important. So these are concepts which are really important to master, not only for this course, not only for the other courses, but for life in general, okay? So I cannot stress this enough. If you understand these things well, it will help you in everyday life. So let's see what this is about. I have two propositions P and Q. Then I have, as we know, the compound proposition if P then Q. Then what we call the converse of this is the proposition if Q then P. Okay, that's the name we give to this new proposition. Okay, the converse of if P then Q is if Q then P. You switch the roles of P and Q. The contrapositive of if P then Q is if not Q then not P. Okay, that looks complicated, right? But this is your friend, okay? And you don't know looking at it that way, but it's a familiar idea, okay? Now, this is like really important. The contrapositive is logically equivalent to if P then Q. So if I flip and negate, it's the same thing as what I started with. Okay, I'm going to discuss this in just a sec. However, the converse is not logically equivalent. That's bad reasoning. This is really bad. Okay, so keep this in mind. Okay, so I'm going to show you some examples here to illustrate this. This is important. So let's start with the equivalence of if P then Q and it's contrapositive, okay? So if I say if an animal is a bat, then it is a mammal. This is correct, right? This is true. So bats are mammals. If you didn't know that, then now you know. I'm telling you for free, a bat is a mammal. It's a flying mouse. So if an animal is a bat, then it is a mammal, okay? What is the contrapositive of that? So I'm going to take the conclusion is that it is a mammal, so that's Q. I'm going to negate that, so not a mammal, right? And I'm going to take that as my hypothesis. So if an animal is not a mammal, then it is not a bat. This is also correct, right? If I show you an animal in a box, the box is closed and I say the animal in that box is not a mammal, then you know that it's not a bat because a bat is a mammal, right? So you see contrapositive and the original implication, that's the same thing, okay? So that's a good example. The converse is not equivalent. So let's illustrate this. So again, if an animal is a bat, then it is a mammal, okay? Now I'm going to look at the converse of this. So now I just flip the hypothesis and the conclusion. So if an animal is a mammal, then it is a bat. That is not true, right? Okay, I'm not a bat, and I'm not Batman either. So if I show you a box, closed box, and I say there's an animal in there, and I say it's a mammal, and you conclude, oh, then it's a bat, well, you're not going to look too smart, right? That's clearly not correct. But if you know that an animal is a bat, then you know that it's a mammal, okay? All right, this may look very silly, okay? But if you look on the internets, you will see zillions of people making these very basic mistakes. It's really horrible, okay? So try to keep those in mind when you're thinking about contrapositives and converses. Okay, to finish this, we're going to reinterpret what we've just done in terms of bits. So there's really nothing new that I'm going to add from a conceptual point of view. We're just going to think of 1 as true and 0 as false, okay? And just reinterpret what we've been doing and to see, so what happens if I just look at true, if I just call it 1 and false, I call it 0. Let's see those truth tables, can we reinterpret them in terms of numbers, arithmetic, maybe. Maybe there's a nice way of doing that, okay? So let's take a look at the truth tables, which are just now tables for 0, 1 tables for negation, or, and XOR. Now, in terms of bits, the symbols are usually written out as not, or, and XOR. Okay, that's like the convention. So what is the not of a bit? You flip it. It's just 0 becomes 1, 1 becomes 0, right? Now let's take a look at the and. Well, I'm just rewriting this. This is the table of the and, right? So and is true, or 1, if both x and y are true. Both are 1. So that's the table. Or, right? Or is always 1 except when both x and y are 0, right? So or is very forgiving, right? So, and the XOR, if you remember, the XOR is just like the OR, but it's exclusive. So it'll light up as true when x and y, one of them exactly is true. So that's how you reinterpret it in terms of zeros and ones. So this is just basically if you take the truth tables in terms of true and false, and you just replace every true and false by 1 and 0, this is what you get, okay? Renaming not, or, and XOR like that, okay? All right. Now, it turns out that if you look at these tables, there's a natural way of interpreting them in terms of arithmetic. So let's take a look at the and, okay? So if you look at this, it gives you 1 precisely when x and y are 1, otherwise it gives you 0. So basically, this is the minimum value, right? If I take the value of x and y and I compute the minimum, then that's exactly what you get here. That's the same as and. Okay. All right. That's the same thing. What about the or? Well, that's the maximum. If you just look at those values, the maximum of x and y will give you exactly the same as the or. So that's pretty cool, right? So these logic operations can be seen when you reinterpret in terms of zeros and ones. One is min, one is max. That's pretty cool. And XOR, now if I had like a few more months, we could go more into that. There's really very cool things to say about XOR, but it's parity of the sum. So if you add, it's almost like plus, but 1 plus 1 is 2. There's no 2, but 2 is even. So we just put a 0, okay? So 0 plus 0 is 0, 0 plus 1, or 1 plus 0, this is 1, and 1 plus 1 is even, so 0, okay? So that's how you can think of XOR. So that's, okay? So you can think of those as operational zeros and ones. Okay. Bit strings. Here, there's nothing new. So basically what we want to do is, so imagine a machine is treating operations rather than bit by bit, you feed it bit strings of the same length, and you want to have it compute the and of these 2 bit strings. What do we mean by this? We mean that we are taking the and coordinate wise or bit wise, okay? Same for or, XOR, and so on, okay? So here's an example of what we mean by this. And yeah, and I remind you, I don't mention this, but you have like tons of exercises assigned in the book, right? These are not to be handed in, but the tests are based on these exercises, not just the WebWorks. That's one thing. Look at the exercises in the book, and you'll see it covers all the material that I'm doing. Okay, so I have 2 bit strings called A and B. A is the bit string 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, and B is 1, 1, 0, 0, 0, 1, 1, 1, 0, 1. You see there are spaces at every 4 bits. It's just to make it readable, more easily readable. easier to read. Yes, thank you. So what do we mean by A and B, A or B, A, X or B? You just take one bit at a time. Okay, so let's start with the AND. So in red, you see, so the AND of 0 and 1. Again, AND is minimum. Okay, so you get 0, you get 1, 0, 0, 0, 1, 0, 1, 0, 0. So the AND of those two bit strings is a new bit string, which is obtained by taking the AND of the corresponding bits. Or, same thing, or is the maximum. So you take the maximum, this is 1, 1, 1, 0, 1, 1, 1, 1, 1, 1. And the XOR, how does it go again? It's like adding the two bits, but if it's 1 plus 1, you get 0. Okay, so this is 1, 0, 1, 0, 1, 0, 1, 0, 1, 1. Okay, so that's what we mean. And so there you have it. Okay, so we've talked about logical equivalence, which means that so two compound propositions are logically equivalent, means they have the same truth table. So you could have two very different looking expressions, but when you compute their truth tables, you get the same thing. We've talked about the contrapositive and the converse, which are useful concepts in reasoning and that you should not mess up. And we've reinterpreted all the connectives in terms of bits and extended our operations then to bit strings. So that's what we did today. And that's the end of chapter 4. And that's it for today. So I'll see you next time. See you. Bye.